We had a sort of a discussion on recurrence last time, and people were kind of confused, or I was confused actually, about what exactly recurrence meant. So thanks to two people who sent me email with some pointers, I want to actually wrap up and discuss exactly what recurrence means. And then that'll just take a couple of minutes, and then we'll get into the stationary distribution of a Markov chain, and then a second theorem which allows us to compute the stationary probability distribution for an ergodic Markov chain. And then we'll move from discrete time into continuous time and continuous Markov chains. And I'll just state some results for continuous time chains, which are really very similar discrete time chains. And then we'll study in particular a specific type of continuous Markov chain called birth-death processes. We'll see how far we can get into birth-death. And then this actually is a basis for essentially queuing theory. Almost all queuing theory, at least elementary queuing theory, can be derived from the analysis of birth-death processes. So let's get into recurrence. The main question in recurrence where I got confused about is we talked about a Markov chain where we have a state, and we enter a state, and then we leave the state, and then the question is, do we come back to that state or not? Okay. And what I said was that as long as there's a non-zero probability that you return, it's called recurrent. Actually, that's wrong. The right way to think about it is that, let's say that you leave a state you never enter, okay? So that's called transient, okay? And if for sure you're going to return, then it's called recurrent. So the way it's sort of whether you have some non-zero probability of returning, the question is whether there's a non-zero probability of not returning, okay? So let me make it a bit more precise. We define the following thing. Let's f I n mean the first time, and of course time is discrete over here, you return to state I after leaving it is n. Okay, steps. So that's called the first passage time to go from state I, well, we're coming back to state I. So recurrence can be defined as in other words, the probability is n steps. Okay, so Fij is a probability. It's a random variable. We're saying that this is the probability that you come back to state I after n steps. And recurrence means that this probability sums up to 1. Okay, it means you're going to come back to it for sure. After some number of steps, you're going to come back to that step. That's what you're saying over here. And transient state means that this, in other words, once you leave a state, there is a non-zero probability that you won't return. So non-zero probability should be thought of as with transient states, not with recurrent states. So transient means you enter a state, you leave it, there's some chance you won't come back. You'll just wander off, and you'll never come back to that state. That one would be called a transient state. Okay? Any questions about this so far? Okay, so if there is any chance that you won't come back, okay, any chance you won't come back, it's transient. If you're guaranteed to come back, it's recurrent. That's the easy way to remember it. And then the second question was, what is meant by, we know that something may recur, okay, but then we have an expectation on how long it's going to take. So we have these two other terms, recurrent null and recurrent non-null. The current null means that the expectation on how long it takes to return okay, is equal to infinite. So one question was, how can you have a Markov chain where the expectation on the number of steps to return is infinite, yet it's recurrent? And here is a numerical example for that. So let's say we have the following Markov chain, and then we have this the following transition probabilities. We come back half, and we come from here, with 1/3, and so on. So the kth step, you come back with probability 1 over k. Okay, now the probability they're going to come back to state 1. Okay, probably going to come back to state 1 is going to be 1. Okay, because you can see this basically some adds up. However, let me make sure I get this right over here. I got this from a pointer from. Okay, so actually I have to be careful. This has to be 1. This has to be so 1 to go here, half to go here, 2/3 to go. Okay, so 0. Let me make this right. 1, 2, etc. So so we can see that f to f0. So you come back in state 1, the probability is 0. You're now going to come back in one step. So the first time you come back is going to be 0. Remember, this is the first time you come back. f0 in 2 steps is going to be a half, so 1 and then half. So you come back in 2 steps, probability half. The probability you come back in 3 steps is going to be half times 1/3. So I get 1 here, half here, 1/3. Okay? And I've set it up so that the probability of taking essentially n steps is going to be, these things are going to show up. So f4, 0 is going to be, for example, half times 2/3 times 1/4, because I'm going to have 2/3 over here. Oops. And this is going to be 1 over 4th. So we set it up so that the denominators and numerators keep cancelling out. So half, 2/3, 1/4, so 2 and 2 cancel out. And we basically get something of the form 1 over k plus 1, okay, roughly speaking. And by the way, I have pointed to this on the website, so you don't need to copy all of this down. But we can show, and I'm going to just skip it in the interest of time, that n equals 1 to infinity f 0n equals 1. Okay, so it's guaranteed to return. However, sigma n equals 1 to infinity n f 0n equals infinity. And the reason is basically because the harmonic series diverges. In other words, this is a result you should know. 1 over n. Basically, this series, 1, half, 1/3, etc., this series diverges. Okay, it's kind of a non-intuitive result because each number is actually smaller than the previous one. 102, 103, 104, etc. And you say, oh yeah, sure, it gets smaller and smaller. Well, guess what? It doesn't get small fast enough. So this series actually diverges, and that is the reason why this Markov chain over here, which I've sketched out, is recurrent, but it's recurrent non-null. So you're guaranteed to come back, but the expectation number of steps is going to be actually infinite. So it's recurrent null over here. I'm sorry, not recurrent null, it's recurrent null. Okay? Any questions about this so far? Yeah?
So if you have a self-loop in state I,
yes,
then there is a non-zero probability you stay in that state forever. All the other states are transient.
Okay, so the question is, if you have self-loop on state I, they have non-zero probability that you'll stay in that loop forever.
But and that probability goes to 0.
That probability goes to 0. Right, so we have to look at so it doesn't mean that it's transient. No, that other states are transient. It's just, because it all has to do with the convergence of the series. If that series, converges essentially as limit goes to infinity, it dies down to 0, then, things are okay. But, so it turns out that recurrence is a very difficult property to prove, okay, for infinite chains. For finite chains, of course, it's straightforward, but for infinite chains, it's very hard to prove recurrence. And so, it's a bit confusing. There's a book on Markov chains by Bremo, and I can give you a more detailed pointer. I'll probably put a pointer on the web. So if you're interested, you can find out a lot more about these chains and recurrence, etc. from the. It's a book only on Markov chains, so there's a lot of detail in there. This example, however, is not from Bremo. It's from an online thing, and I have a pointer to this, so you can look at the details as well. But this particular divergence of this series, just as a historical footnote, was proved by Bernoulli, not the famous Bernoulli, but his brother, I think Jacob Bernoulli, I can't remember the first name of Bernoulli, but his brother Daniel Bernoulli proved divergence of this series. And it's kind of an interesting historical sidelight that this is a divergent series. Okay, any questions on this? All right, so this was just kind of clearing up some questions from last time. And hopefully, Ali, this answers your question. And also somebody else was asking about, can we have a recurrent non-null chain? Well, that's a recurrent non-null chain. Okay, moving on. I'm going to come back to the notion of stationarity, because that is a very important concept. And then we'll talk about this kind of a plug and chug approach, as they say, to computing stationary probability distributions. So what does stationarity mean? Yeah, just a second. All right. Yes?
I think these definitions can be the same. I mean, if that probability is not zero, then in limit it goes to be 1 for sure.
Which probability is not zero?
First we said that it is recurrent if it's non-zero probability to return to that state. I say if it is not non-zero, then for sure it would be
1. I don't want to mess up the definition, okay? Maybe. As I said, the recurrence is a bit tricky. There are some pathological cases, okay? And I don't want to go down that path. All we need to know is it transient or not? If it's transient, there's some chance you won't come back. And if it's not transient, it's recurrent. And then there is guarantee you're going to come back. You're saying, well, if it's not transient, it's sure to be recurrent. Yes, that is true. Okay, so, but then you're saying, is there a state which you cannot prove that it's not transient because it's, well, okay, the logic gets a bit crazy here. I don't want to go down their path. Okay, let me come back to stationarity, because that I think is a much more important concept. The notion of stationary probability distribution for a Markov chain is this. We have Markov chain, and let's go back to the analogy of person climbing up the stairs, up and down. So here's somebody going up and down these stairs, up and down these stairs. And what we want to do is this. We want to say, okay, I'm going to take a snapshot at a random point in time. I'm going to pick an arbitrary point in time and say, okay, where is this person? And I want to give you some expectation of which steps they're going to be. And it turns out that, if certain states are preferred, okay, and we'll see what that means when I do an example, if certain states are preferred, it's more likely that person is going to be on that step, right? So it's not an unreasonable question to ask, if I take a random point in time, which state are they on? Because we'll actually hopefully find out which state they're on. So stationarity of a Markov chain or stationary probability distribution really answers the question, okay, if I just take an arbitrary point in time, what state is that process at? In other words, if I take let's say I want to look at the random variable xn, let's say x50 for the sake of argument. I don't know anything about the initial probability distribution. I don't know exactly where you started from, but at time 50, if I don't know anything else, where is this person at? I want to tell you the distribution of x50, okay? More precisely, let's define the following thing. Pi jn is probability that xn equals j, okay? So we're saying that at the nth time step, the Markov chain is in state j, which is equivalent to saying that the xnth random variable in the family of random variables has the value j, okay? So these are two different ways of representing the same concept. This one says, I have a random variable that assumes the value j. So in the trajectory, at time n, it's got the value j. Alternatively, we can think of this as saying the stochastic process of the Markov chain at time step n has state j, okay? Because these are equivalent ways of saying the same thing. So this is a representation. What we want to do is to compute basically lim n tends to infinity pi j n. In other words, as we have the number of steps going to infinity, what do we call it? And we'll define this, we'll give it the name pi j. In other words, the dependence on n has gone away. That's called the stationary value of the probability of the Markov chain being in state j, okay? So again, it's the same thing. All we're saying is that now we're saying time has gone into the future, all history of the past has been forgotten. What's the probability I'm going to be in state 5? What's the probability I'm going to be in state 6? What's the probability I'm going to be in state 7, etc. for each of those states? And that we denote by pi j. Okay? So to make this very clear that we are talking about the limit. So if I tell you what is pi 1, what is pi 0, 1, that's probability of being in state 0 at time 1. What's pi 0, 2, probability of being state 0 at time 2, etc. These are very dependent on initial conditions. But if the system is ergodic, we're going to forget all of this stuff. And after a while, no matter where you start from, no matter which step you start from, you're going to enter into the stationary probability distribution. Okay, and it's actually a quite interesting thing to take ergodic Markov chain and start with different initial steps, and you'll find that very soon you'll actually converge onto this over here. Okay, so last time we kind of gave an intuitive understanding of stationarity, which I'm continuing over here. Now I want to give you essentially a theorem on stationary probability distribution. Okay, so before I do that, I want to make sure everybody's on the same page. So does everybody get this? Are there any questions about this? Anybody? Okay, so what we want to do is we want to compute pi j, all right? So we want two things. First, we want to know that such a thing actually exists. In other words, if I give you a Markov chain and say, okay, compute the stationary probability distribution, how do you know it's there? I mean, how do we know that the stationary distribution is in fact even there? It might be that, the probability distribution oscillates. Okay, so if on every even step, you're very likely to be in state 0, and in every odd step, you're likely to be in state 1. So if you have a periodic Markov chain, which has two states, maybe the probability distribution changes every state. Every step, your probability distribution changes. So how do we know that we don't have that? Well, if you say it's aperiodic, then I won't have this periodicity problem. Well, the second thing is, how do I know I can actually be in some state? How do I know that pi j is not equal to 0 for j equals 20? If I have a 2000 state Markov chain, how do I know that, I'm never going to reach some state? Again, if I have an irreducible Markov chain, I know every state can be reached by every other state, then I know that every state is going to have non-zero probability in the stationary distribution. So again, I can do that. And the third thing is I have to worry about, time dependence. So I have to guarantee it's homogeneous. If it's not homogeneous, then the stationary distribution doesn't even exist because everything depends on time. Time changes, the transition probabilities change, and then I don't have stationarity. So the second fundamental theorem, which is this over here, really gives us the criteria for us to decide whether or not a given stochastic process even has a stationary distribution. And moreover, condition ergodicity, it will tell you a technique, an actual set of equations you can solve to find the stationary distribution. So let me state the theorem. It says, okay, so it says in an irreducible, so we're going to make sure that we can reach every state, and aperiodic homogeneous Markov chain. Okay, so I've stated these conditions. I'm going to get rid of all the pathologies, right? I said all these conditions are pathological conditions. Let's get rid of them. If I have this, then the limiting probabilities pi j equals, and this is exactly the same thing as before, n tends to infinity pi j n exist. I should probably put, just to be consistent, always exist. So the first thing is it's existing. Okay, so we know that these probabilities exist. Okay, we haven't said anything about what they are. We're just saying it exists, and are independent of initial distribution. So again, I'm saying that these limits exist, and now I'm telling you something stronger. I'm telling you that it doesn't matter where you start from, these limits will be reached no matter where you start from. So I can say you start on step 5 or step 4 or step 3 or some probability distribution. On these steps, it doesn't matter. In the limit, these things will always exist and will be found. Moreover, if additionally all states are ergodic. Okay, so we have ergodicity, which means that we have the recurrent non-null. Okay, we need to, because we already got aperiodic and irreducible, okay, and homogeneous, so we just have to have one more condition, which is recurrent non-null, then you get ergodicity, right? In that case, they are uniquely, the pi j is greater than 0 for all j, okay, and moreover we have a following system of equations which give us these values, which is, this is the equation set of equations, sigma j pi j equals 1. Well, that one is trivial. Obviously, it means that, you know, the probabilities sum up to 1. And here's the interesting one. It says pi j equals sigma over sum over I pi I p I j. So basically, what you're saying is, let's look at all the ways that we can reach j, state j, from any previous state I. All right? We can find all the ways we can reach I. Then we multiply that by the probability of being in I. So let's say I have a probability 0.5 of being in state 1, and then I have some transition probability of going to 1 to 2. Then I will multiply those two, and that will tell me, and it'll sum across all the different ways, and that will give me the probability of being in 2. Now, see that this is actually a system which is sort of self, you know, so pi 1 is represented in terms of pi 2, pi 3, pi 4, pi 2 is represented in terms of pi 1, pi 2, pi 3, etc. So it's a self-consistent equation, and when you see this kind of thing, immediately you should start thinking about what is the fixed point of the set of equations, and without going into the math of this, but you can easily see that if it represents this as a matrix, this essentially corresponds to the eigenvalue of the matrix. But since I'm not assuming you guys know linear algebra, I'm not going to state it that way. Instead, I'll just do an example and show you how this works out from the example. But for those of you who are familiar with eigenvalues, this is just an eigenvector computation. It's a 6-point computation. Okay, it just falls out pretty naturally. So let me go back to this Markov chain over here, and then we'll just do it. So, all right, so what are we going to do? I'm going to draw this picture over here. So this was a 3-state Markov chain. On your notes, it's on page 10. Oops. And we have a self loop at point 2. We've got point 4, and this is point 4. And then from 2, we had a probability 1 going here, so 0 and 0. And then from 3, we had a self loop of 0.25. Probability going to 2 was 0.25, and probability going here was 0.5. Okay, so just looking at this, you kind of see that if you're in 2, you're going to go to 1 for sure, and if you're in 3, the probability half, you're going to 1. And if in 1, you kind of leave it with probability 0.8, which is 0.4, 0.4, but you kind of go back to 1. So in some sense, we expect that you're going to have a higher probability of being in state 1 than in probability of being states 2 and 3. Okay, just from kind of looking at this, saying, okay, you know, you're being pushed into 1 from both 2 and 3. In fact, if you get to 2, for sure you'll enter 1. So we expect the stationary probability of being in 1 to be higher than of being in 2 and 3. Okay. So let's check if the conditions apply. So here are the conditions that we need to apply over here. Okay, how do we apply it? So here is sort of a checklist, you know, for the engineer. This is a Markov chain. Can we apply this theorem or not? So the checklist is, first, you'll check whether is it Markov. Okay, in other words, does memorylessness hold or not? Well, I already told you it's a Markov chain, so this one is okay. The second thing is it homogeneous? And we'll say, yes, it is, because these transition probabilities, Pij, are not Pijt. If you don't have a time dependency, these are transition probabilities independent of the time probabilities. Kamran, you may want to come over there, otherwise you're going to see nothing at all. You can just come in the front. There's a chair over there already. Oh, you're just going to sit there. Okay. Is it homogeneous? Yes, it is homogeneous. Then, I remember I said earlier that if it's a finite chain, then we get essentially recurrence. So I'm going to just say it's finite. Yes, it's finite. You can see that. Is it aperiodic? Well, I have a self loop. And if I have a self loop and it's irreducible, I get aperiodic for free, so it's aperiodic. And is it irreducible? Yeah, it's irreducible because you can see I can get from any state to any other state. So I check that. Whoops. At this point, all the tests are met. Okay, at this point, just by pure inspection, I can tell you that every state here is ergodic. Okay, and so these conditions of irreducibility, being aperiodic, homogeneous, recurrent non-null. Instead of recurrent non-null, it's easier to check finiteness. All of these conditions hold, and so I can essentially, as I said, plug and chug. So how do we do that? We can just write down the equations like this. What are the equations? Well, we know that essentially pi 0 plus pi 1 plus pi 2, or sorry, pi 1 plus pi 2 plus pi 3 equals 1. So that's no big deal. And the second one we'll start writing down is to express it. So you can say pi 1 equals what? How do I get 2 pi 1 from pi 1? Well, it's 0.2 pi 1 plus, how can I get from 2 to 1? And probability is 1, so it's just pi 2 plus 0.5 pi 3. Okay? Because it's pi 3, I have a 0.5 arc, it's 0.5 pi 3. Similarly, pi 2 equals 0.4 pi 1 plus 0 pi 2, the self loop is 0, plus 0.25 pi 3, and then pi 3 equals 0.4 pi 1 plus 0 pi 2 plus 0.25 pi 3. Again, you can verify all of these from this thing. And if we solve this, we find that pi 1 equals 15 by 31, pi 2 equals pi 3 equals 8 by 31, and of course, they add up to 1. All right? So you can just solve this and see. Interestingly, 2 and 3 have the same stationary probabilities, even though they're not actually symmetric. It doesn't look symmetric, but in fact, it turns out to be the case. Unless my math is wrong, it is in fact correct. Oh, somebody sent me mail saying they verified this. So Sukant, yes, thank you. I did check it too. But yes, so this is clearly, so this is, as you can see, if you can have this checklist right in front over here, you know, my checklist, Markov, homogeneous, finite, aperiodic, irreducible. These are all things you can get from inspection, just from looking at the chain. Yep, all of these are met. At this point, you can just plug these equations in. If you want, you can put it into a matrix solver, solve it, and you can just do Gaussian elimination on this, and you can get the values out over here. And the theorem over here, this theorem, the second fundamental theorem, says these limits exist, and what's more, these are the stationary probabilities of this Markov chain. So given any chain, I can actually just plug and chug. Any questions about this so far? Okay, this is fairly important because in any system where they can model as a Markov chain, you can verify the checklist. At that point, you can just essentially write down without any further thought what the stationary probabilities are. Why is this useful? What we'll find out is that many properties of Markov chains are related to probabilities of being in different states. So if I know the probability, just to give you a simple example, if I can tell you that over here I have some probability, some property, here I have some property, here I have some property, then what I can do is I can take that property, multiply by the probability, I can tell you the expected value of that property, whatever the property is. For example, let's say this represents the state of a traffic signal. It's red and orange and green, and I can tell you the transition probabilities over here. And then I can tell you that if at a random point in time I look at the traffic signal, what is the probability it's red? Well, I can tell you that state from over here, but if you have additional properties that associate with those signals, for example, when it's red, the traffic velocity is 0, right? When it's green, the traffic velocity is something else. It's orange, it's something else. I can give the mean traffic velocity going through the traffic signal, okay? Simply by looking at the stationary probability. So but once you start associating properties with the states, then the stationary probabilities, you can just read off the values, the expected values of those properties from this from the Markov chain, okay, from the stationary probability. So that's why it becomes very useful. And I'm not going to go into that again. This is just the foundations, but you can see why it can be used in practice. Okay. Any questions about this over here? Okay, so I'll take a break here, come up here, and then after the break we'll go into continuous time discrete state Markov chains. I think somebody had asked, is continuous space same as continuous state? Yes, the state and space are used interchangeably, and I think I use them interchangeably as well. Let's come in for this chapter here, which is residence time. I wanted to talk about that. All right, so let me just talk briefly about mean residence time in a state. So we saw that given a Markov chain, we can compute the stationary probability distribution. We can figure out what's the probability that at any random point in time we're going to be in that particular state. So let me go back to the example. I won't put the numbers in, but we had sort of a directed graph that looked like this. And so we saw that we had a higher probability of being in state 1. Now, intuitively, if I have a higher probability being state 1, okay, I mean, I can give you an example. Let's say I have a self loop with a 0.9 self value over here. Chances are pretty good I'm going to stay in the state a long time. Okay, I'm going to stay in, because I'm going to come back round and round and round and escape from it only rarely. Okay, so the mean residence time in this state is going to be much higher than a mean residence time in this state, probably, right? Because it's very low probability I'm staying in this state. I'm going to just kind of jump out of the state. And we saw in state 2, with probability 1, it was leaving the state. So it's got 0 chance of spending any time in the state. It comes in, and the next time step, it's gone out, right? So how do we quantify this notion? It turns out it's very simple to quantify it, because we know that we have this transition probability Pjj. Well, probability Pjj is the probability that in a particular time step we stay in the same state, because Ij is the transition probability of going from I to j. So Jj is the probability you stay in the same state. Okay, so so this one is, let's call the state 0. This is P00 equals 0.9. Okay, so let's think about that for a second. I'm going to be in this state. When 0.9 I come back. Okay, what's the probability I go around twice? Okay, what would that be? 0.81, okay. Why can we multiply it? Because it's memoryless. We come back, once we return, I have no memory of how I got to that state. It was just as if I got there ab initio. I got there in the start, right? Because of memorylessness, it turns out that I can just write down the probability of being in a state for m steps. So probability that you're in state j for n steps is nothing more than Pjj to the power m times 1 minus Pjj. Right? I mean, of course, I've got to leave that as well. Okay? So I have to go around. If I want to be at m steps, I have to be there m times, and then I've got to leave. Okay, so that's why I have the 1 minus Pjj over here, just to get things properly done. And this, if you look at it, is just exactly a geometric distribution. Okay, what is a geometric distribution? Remember, how many failures till the first success? So I can think of the return to the state as being a failure, and this is success. Okay, so I'm going to fail. Let's consider being in the same state as failure. I have failure, 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 failure. These are independent, identically distributed trials. So I have IID, which is what I want. At that point, I can say, oh, this is geometric. And that immediately tells me that the expected residence time is nothing more than 1 over 1 minus Pjj. Okay? Just from the expected value of a geometric distribution, I can just kind of read that out. So The geometric distribution has, again, a very intuitive meaning, which is that I have this memorylessness property. So geometric shows up when you have memorylessness. In other words, in geometric distribution, the fact that I've failed 20 times doesn't affect the chance that I'll fail the 21st time. Okay, I have no memory of the fact I've already failed so many times, because it's independent trials, right? If they're dependent trials, yes, it makes a difference, because so geometric has this property of independence, which means that the past failures do not affect future failure. Okay, and of course we want our students to be non-geometric in their behavior. That means you take the course, you give an exam on Markov chains, you fail. Okay, give you second day, you fail again. Third day, when you exit the course, you still have the same probability of success as on the first day. That means your memory is 0. Okay, so geometric students are hopeless. Okay, I mean, they may as well not take the course because they're not improved the probability of success. These are, easy to analyze, because I can tell you, you entered the course, you exited the course, your probability of success is still the same. Okay, so it's a very bad thing. So memorylessness does not go well with being a student. Okay, all right. So you're looking for a chair? There's one right up in front over here. However, I can assure you that your probability of learning anything from this class is almost 0, because you missed the first part. Okay, so I'm going to finish with residence time and go into continuous time chains. So I want to first start with what is the intuitive meaning of a continuous time Markov chain in the first place. And I sort of mentioned it, but I want to give you a better understanding. So going back to the example of somebody working on the steps, it's still discrete space. It's still discrete space. So I still have steps. Okay, it's not like it's a ramp. It's still the steps. However, I'm now going to allow that person to ignore the clock and just say you can go at any time. You can go up or down at any time. If you start thinking about the continuous time, it's easy to get confused and think, oh, well, what's going to happen? Do I have to worry about all possible time instants? No. What you think about is this figure over here, where I have the specific trajectory of states, and then I have this undefined future. What I can do is, I know that these transitions happen at specific points in time. This is T0, T1, T2, Tk, whatever, Tn. And okay, let this be Tn minus 1, this is Tn. These transitions have already happened. It's past history, so I don't have any uncertainty about it. I know that at so-and-so time these transitions happen. Now what I want to do is, I want to figure out for the future, given this past history of transitions, what is going to happen in the future. And I have some expectation that the transition happens here, or here, or here, or here. Okay? But that's not a big deal. That's just a continuous random variable, okay? That's just a continuous random variable like a exponential, which is actually what we'll use, but it could be any continuous random variable. We're just saying, what is the value, what's the probability that the random variable assumes something of this length? Of course, any precise length, probability is 0, right? We already saw that. Instead, what we can do is we can look at some region delta t, and we can tell you what is the probability that the transition happened in time t and t plus delta t. And of course, that's just a standard continuous random variable. There's nothing funny going on over here. So again, just to repeat, the standard mistake that students make over here is to think that the past could be anywhere. No. The past is what has already happened. These transitions have happened. We've already got these guys over here. We have n transitions happening. Those n time steps are already happened. We've already got those locked down. We're just looking at the future. So it's really the uncertainty in some sense is just in one random variable, which is the n plus first. Okay. So if you think about it that way, then we can write down the Markov property simply like this. The probability that x n plus 1, sorry, x t n plus 1. Okay, and let me make sure I've got this. I have a typo in the equation. The parentheses are in the wrong place. Okay, I'll just make a note of that. The equation, okay. So let me go back and say, earlier in the discrete case, we had the random variables x1, x2, etc., right? In the continuous case, we have random variables xt1, xt2, xt3, etc. So these random variables are associated with these time instants. Okay, so the probability that xtn plus 1 equals j, okay, given, no, actually it's, yeah, this xt, yeah, it's x, how should I put this, xt1, we don't need the parenthesis at all actually, you just see probability xt1 equals j, conditional on x or, what am I doing over here? Okay, continuous, I'm going to represent this. I don't want to put subscripts because then I have subscript and it's too small to see. That's why I'm using parentheses over here. So all right, so let's make this proper. Xtn plus 1 equals j, conditional x t1 equals I1, x t2 equals I2, x tn equals in. Okay, so what am I saying over here? I want to know the value of, so I should say xt1, xt2, this is x tn. Again, you can make x sub t sub n if you want to, it's just kind of small, too small. The notation is not super important. What you're saying over here is that the probability that the random variable xtn plus 1 takes on the value j, okay, that is, we're taking the state j, conditional on the trajectory, that is, t1 is an I1, at time t2 into I2, at time 3n we're into in, that's the trajectory over here, is equal to the probability that x tn plus 1 equals j, conditional on x tn equals in. Okay, so if we can just ignore all the past history, so again, just like we did in the discrete time case, this, everything here, we don't care about. This is all past history. As long as we know the value over here of the random variable at the tn time step, we can tell you, I can tell you the conditional probability that tn plus 1 takes whatever value it is. Okay, and it's a continuous random variable over here. Okay, so that's the, so in other words, the future depends on the past only through the current state in. This is the current state over here. Okay. Any questions about this over here? Okay, where did I go to page 8 here? There's minus 617. Okay. So once I define this, this is very similar. You should compare this, later on to the discrete time case. You'll see where the differences are. There I had x1 equals I1, x2 equals I2. I went from I1, x1, x2 to xt1, xt2. That's really the change that happened over here. Again, don't get confused. All we're saying is that these transitions, t1, t2, etc., discrete points in time happened, at those times. It's a past. Okay. All right. So given this, we can immediately start defining the same set of things. Homogeneity. Well, what does homogeneity mean? Homogeneity means that these transition probabilities are time independent. Okay. In other words, if I go from state I to state j, I can define either pij, just like I did earlier, and these probabilities time independent. Then I can I'll call it a homogeneous continuous time Markov chain. We can talk about irreducibility. We can talk about ergodicity, aperiodicity. They're all the same thing. Okay, recurrence. Why is it the same? What's going on is that we draw the continuous Markov chain, continuous time Markov chain, using the same kind of figure. Okay. All I'm saying now is that I can go between these states, okay, at arbitrary points in time. It is not clocked. So these properties are all graph properties. Okay, these are all essentially graph properties, and the graph properties are independent of whether the transition times happen at discrete times or at continuous times, and therefore we can just use the same exact definitions. There's no change in definitions at all. Graph properties are graph properties. This is just a continuous time graph. Yes?
So basically, what's the difference between continuous time and discrete time? Because you are saying that in the continuous time, we again have only information about certain specific times, so we have discretized.
In the past, but not the future. The future over here is continuous. In other words, for example, the residence time in a state is not going to be geometric anymore because it's going to be continuous, and it will become exponential. I'm going to come to that. Okay, why don't you hold on to the question for just a couple of minutes. I'll talk about the things where it is different, and then you'll see where it's different. Okay, but graph properties are all the same. Graph properties are the same. Okay, so let me do one thing, and then we'll take a break, which is I'm going to talk about the mean residence time, just as an illustration of continuous time, how it differs. So I should say mean residence time. So mean residence time in a state is basically, you can show that it's exponential, not geometric. And the way to look at it is the probability that, okay, let me just give you some notation first, otherwise. Residence time in state J, let's call that R sub J. Okay, and this is again in the sort of in the limit. So probability, actually we don't even need the limit. R sub J is greater than S plus T. Given that Rj is greater than S equals probability that Rj is greater than T. Okay, if I draw this picture over here, this is time. And, okay, so I can draw this something like this. So given that it's a S plus T, and this distance is T, I'll take the same distance T over here. So what I'm saying is that I'm in some state J, okay? Some state J, and I've told you that you've already been in state J, in that state for S seconds. Okay, I've already told you you've been in the state for S seconds. I'm going to ask you, what is the probability you're going to stay there, let's say 5 more seconds, okay? Then the conditional probability of being in that state for 5 more seconds is as if you didn't know that you've been there you've been there for S seconds. It's as if somebody asked you right at the beginning, and you said, yep, that's a probability. And if you see this equation, this is exactly the memorylessness property. It says, I don't know how long I've been in the state. I know no matter how long I've been in the state, the probability of being there for 5 more seconds, okay, is this. It's this value over here. So the conditional probability, that is being told you're being there or not, doesn't make any difference. And this is exactly the property of exponential distribution. And so memorylessness of the Markov chain directly gives you, without any further math, it gives you right away that this property must hold. And if this property holds, basically by definition of Markov property, then it also means that the distribution of the random variable corresponding to residence time, Rj, is going to be exponentially distributed. And this is again similar to the notion of geometric. Intuitively what's going on, and this is a very important intuition to have, is that in each infinitesimal period of time, there's a constant rate of you leaving that state, okay? And equivalently, it's a constant rate of you staying in that state, okay? So the Pjj, which is the probability that you stay in that state, over some small period delta t, you're going to have a constant rate, not a variable rate, a constant rate, and that translates to, in the limit, an infinite number of geometric trials, okay, where each trial has an independent, identically distributed probability of success or failure. So, and when you take that limit, basically what you get is the exponential distribution. So this hopefully answers your question. Okay, what is different in continuous and discrete? In discrete case, we have this notion of trials, which are independent trials, okay, of you staying in a state or not staying in a state. Instead, over here, we have the equivalent continuous time probability, and we can look at the probability that in time t and t plus delta t, what is the probability you're going to leave? If you just plug in t plus delta t, what you get is sort of the constant, which is just the slope, okay, which is just the decay rate of the exponential distribution. That is the constant probability that in time t plus delta t you're going to exit that state or stay in that state. Okay, so we have this exponentially distributed random variable describing the mean residence time in the state. Okay, so if you remember your exponential distribution and memorylessness, you'll see that it relates directly to the Markov property of the continuous time Markov chain. Any questions about this over here?
So when we represent a continuous Markov chain with a diagram, we don't have self-loops, right? We don't show it. We just have the loops out of that state.
I'll come to that. You actually do have self-loops in the state transition probability diagram. But in the state transition rate diagram, you don't have self-loops. Okay, so there's a difference, a big difference between the state transition probability and the state transition rate. Okay, and after the break, I'll talk about that because that is actually pretty important. But there you don't draw self-loops because the rates are different from probabilities. So the way you go from probabilities to rate is you take the probability multiplied by delta t, that gives you the rate. Okay, and then in the rate it turns out you don't need self-loops, in the probability you do. So this is I'm still drawing probabilities, I haven't come to rates yet. Okay, any other questions about this? Okay, let's pause. I can see everybody's eyes sort of glazing over, and that's always a good sign. It means that irreducible means every state can be reached from every other state. Okay, all right. Now, if you're not irreducible, okay, means there's some states that cannot be reached from some other states. Now, it's possible that we can have a Markov chain that looks like this. Okay, I mean, basically, all the states go into this one state and never come back. So these states clearly are not reachable from each other. This is a reducible Markov chain. All right. Now, the example I gave earlier was like this. We had this sort of odd and even states business. Okay. So this one is called a separable Markov chain. Okay. It's a separable Markov chain. I can separate out the Markov chain into two subchains which are each irreducible. Now, in the definition that's in the notes, I'm confusing reducibility and separability. So this is irreducible. So this is reducible. That is reducible. This is separable. This is not separable. Okay. So that's where it gets a bit tricky. So you'll be careful. And I was mixing up the definition of separability, and so I was mixing up the definition of separable reducible chains versus non-separable reducible chains. This is non-separable reducible, and this is separable reducible. Okay, so it's yet another exotic little thing. Again, in real life, when you're trying to do something, we want to get rid of all the pathologies. So we'll just kind of figure out that, yeah, every state can be reached from every other state. If you can't, then, well, it's not practically important. It's just irrelevant. You can say, well, we can't use queuing theory, and you would be right. Or at least you can't use elementary queuing theory. You have to do something complex, which is beyond the scope of this course anyway. Okay, so already you're in big trouble if it's not irreducible. Okay, so you're walking through a forest and you see this, and you take out your guidebook. Yeah, is it reducible? Is it green? Does it fly? Yes, yes, yes. Okay, my gun will work. You shoot it. Okay, or capture it. It's a dart gun. You're not actually killing it. I don't want to condone killing of exotic fauna by means of guns. It's just tranquilizing gun. However, it says it's green, but it doesn't fly. Now you're in big trouble. You better hide. Okay, you need to go get some different equipment because you might be eaten, and this is things that will eat you. Okay, it doesn't matter whether they are separable or not. They're going to eat you anyway. So. Okay. This is the guide for things that are not bad. These are things that are nice. Okay, so we are now ready to start looking at something more interesting, which is so in a discrete time, discrete space Markov chain, which is what we've been looking at so far until the last little bit. Stationarity turns out to be an interesting property. All the prior work was simply to be able to get to the point of stating the second fundamental theorem. Okay, because that is the theorem you need, and you need all those definitions, of all the pathologies, so you can exclude them. At that point, you can start saying, okay, I have a Markov chain, the checklist, everything is done, now I can do stationary probability. In exactly the same way, it turns out that we can state a theorem for continuous time Markov chains, which looks a bit similar but is not the same, and I'll explain what is the difference. And what we're going to do now is to look at the stationary probability distribution for a continuous time Markov chain, and this is what we'll be using from now on. Was the question? No. Okay. Okay. So I'm going to kind of give you the statement without proof, of how to find the stationary probability distribution. It follows from a similar theorem. Okay. So first, I'm going to define Pijt. Okay. This is the time dependent okay, sorry. Okay, so I'm saying if the random variable x at time s is I, in other words, the Markov chain is at state I at time s, then Pijt is the probability that it's at s plus t, is at state j at time x s plus t. Okay, this is essentially nothing more than the random variable xs plus t, okay, defined in terms of a density function. Okay, of course, for any specific value of t, it's going to be 0. However, what you're really looking at is the range t plus delta t, as we would in a continuous time, in a continuous random variable. So that's the first definition. Then we're going to define a new quantity called Qij, and this is different. This is the rate. Okay, and remember I said that in a Markov chain we have this we have a constant rate of going from one state to another state. That rate is called Qij, and it's defined like this, as limit delta t tends to 0 Pij delta t over delta t. Okay, it's basically the limiting transition rate of going from state I to state j. Okay, and because the probability goes down, and also by dividing by some value that goes down, this can be a large number. It can be like 20 or 200 or whatever, 5,000, right? It doesn't have to. It's not a probability. It's a rate. Okay, again, you should be careful to remember that Pij is a probability, Qij is a rate. Qij is just it's a positive value, but that's all we know about it. We don't know that it's smaller than 1. And we define Qii. We will define this to be in a special way. Now, Qij is a rate of going from I to j. What is the rate of going back to your own state again after some time? We're going to actually, what we're going to do is we're going to make this sort of a funny definition. We'll do it in this way because it helps us later. This is going to be defined as limit delta t tends to 0 P I delta t minus 1 by delta t. Okay, so all right, so this value Pii delta t is going to be a fairly small value, and this is minus 1, so this is a negative quantity. So Qii is always going to be a negative quantity, all right, and can be viewed as the negative of the rate at which you stay in the same state. Okay, it's not the rate which is not the rate, but the negative of this rate. And the reason we do it like this is because we can see, if you do this, we know that, okay, we know something. We know that these are probabilities. So sigma sum over j Pij t equals 1. So this is, okay, we know that at any time it's going to be the case that either I'm in some state or move to some other state. So these probabilities summed over I are going to be 1, and this immediately means that if you plug those values over here, Pij and delta t, and you come in over here, well, what are we doing over here? When we sum over all the i's, we're going to get some quantity over here, and this is a negative 1, so it will turn out, obviously, that sigma j q I j t equals 0. Okay, So actually this is not J, this is sum over J. Did I make a typo there? Yeah, it's sum over J. So because the probability of my leaving some state or staying in the state is going to be 1, the sum of all this is going to be 1. If you just put that over here, you'll find that the rate, the Qij rates, are all going to sum to 0 because I put this -1 over here. All right, and that's kind of a nice property to have. Okay, that's, I think, the question you asked: do we have the self? Okay. For now, we're just writing it down. When you start writing down the state rate transition diagrams, you'll see how this works out. But for now, I'm just kind of giving you the mathematical definition over here. So again, for continuous time, we will not focus on the transition probabilities, but we'll actually focus on the transition rates. And the reason is the following. Okay. Once we define the Qij in this fashion, which is the then we can immediately write down the probability of being in state J at time t. We will denote that as Pjt. Pi jt is the probability of being in state J at time t. This is very similar to pi jn that we had earlier, except now we have a conditioning. Now we have it as a function of time. We can write down from the equivalent of the second conditional theorem. We can write down this: d pi j t by dt. The rate of change of being in the state is given by Qjj pi j t plus sigma k not equal to j Qkj. Oops. Okay, so what we're saying over here is that the rate at which I am going to, rate at which the probability of being in a state changes is given by the sum of these two things. Okay, this is in some sense the negative of the rate of leaving my state plus all the rates coming in, because if I look at k not equal j, this is the probability of being in that state over there, and then this is the transition from k to j. So if I take the product of these and sum it up, this is all the sort of the flow of probability into state j, and this is the outflow of probability out of state j, and these rates then give you the rate at which the probability itself changes. So what I'm doing here is a little bit funny, because so far we've been thinking of events and probabilities of events, but with Markov chains we have to actually think not just of probability of being in a state, but at the rate at which the probability of being in a state changes over time, which is nothing but d pi j t by dt. Okay, so just to give you an example, let's say d pi j t by dt turns out to be -1. That means the probability of being in a particular state declines over time. Okay, obviously we can't have it go to -1. It can't go negative, right? It's a probability, but this is the rate at which, at a particular point in time, the rate at which the probability of being in a state is declining. Okay, so we have these things over here, and if you solve these equations, these are essentially nothing more than first order differential equations. You can solve them using standard first order techniques. We will find out the probability, the resistance times of being in different states, which is just pi jt. Okay, to solve these for general systems turns out to be quite hard. You have to go into essentially Bessel functions and things like that. Instead, we will focus on ergodic. So this is not for ergodic. This is for any Markov chain. For ergodic Markov chains, we have a much simpler result. We can say that the limiting probability, the limit probability pi j exists independent of time, exactly in the second theorem. Moreover, to find pi j, we can just use these equations, which is that Qjj pi j plus sigma k not equal to j q kj pi k, oops, equals 0, and then sigma. Okay, so This looks a lot like the equations we saw for the stationary probability distribution of a discrete time Markov chain, except that now these are being expressed not in terms of probabilities but in terms of rates. Okay? So what we're saying over here is that this qjj pi j plus all these things over here. Now this, if you look at this and compare it over here, this used to be d pi j t by dt. In stationary state, what's going to happen is stationary probabilities are such that these rates are zero. Okay, we have some kind of balance. What's going on? We have some flow of probability coming into some state. We have some flow of probability leaving that state. If you're in a stationary distribution, then these probabilities must balance out. So all the net inflow, which increases the probability of being in any particular state, must balance out the net outflow of leaving that state. And if you do this, okay, the probability of being in that state doesn't change. Okay, if you think of the probability as being kind of water, okay, just for the moment, think of probability as being like water and the state as being like a vessel. I have some flow, I have some faucets open. So each faucet that is, so I have, let's say I have a vessel called, j equals 1, and I have, let me see if I can draw a faucet even. I'll draw a two-dimensional faucet, which is much easier than a three-dimensional faucet. Okay, and let's say we have two faucets coming in from j equals 0 and j equals 2. Okay, and then I have a drain over here. Okay, so this stuff is coming in to me at the rate q01, and this stuff is coming in at the rate q21, and it's going out at the rate q11. Minus q11 is the rate at which, actually q11 is leaving. Okay, no, I take it back. It's q12 plus q10 is the rate at which it's flowing out from this vessel. All right, and what I'm saying is that if you're stationary, okay, then we want to look at the probability of being in this particular state, which is nothing more than pi 1. It must be the case that the total amount of probability flowing in should match the total amount of probability flowing out. And therefore, we get the right-hand side of the equation to be 0. Okay? And this gives us a stationary probability distribution for a continuous time Markov chain. Okay? And again, you'll see that this is different from a discrete case. In a discrete case, the equivalent representation over here was basically looking at Pij, whereas here we're looking at Qij, rates rather than probabilities. Okay. Any questions about this? Okay. I've kind of been a bit fast on these terms because it turns out that really what we care about are just these equations. This equation over here is all we care about. Okay. Because you'll essentially be looking at ergodic continuous time Markov chains. And to be even more honest, we did all the definitions of Markov chains so that we could get to the stationary probability distribution of a discrete time Markov chain. We actually did all discrete time Markov chains just so that you have some intuition to study continuous time Markov chains. Okay? And all of this stuff in continuous Markov chains is needed just so that you can understand what a birth-death process is, and we'll actually then make this even simpler for birth-death processes, which is the next topic. And so, we have to kind of walk through these fairly complex definitions and so on and so forth, just so that we can start studying birth-death processes, which is in fact what we'll be studying for the rest of this chapter, pretty much. Okay. Any questions on this so far? Okay, so I can see it's about 8 to 10% of the course of the class is sleeping, and the rate at which this is going up is approximately 1 every 3 minutes. So that's the rate of change of sleepiness. So I'm going to try and wake you up by telling you that the class is ending in 15 minutes. So that should wake you up. And the second thing I'm going to do is to tell you about birth-death processes. And this is kind of one of the center points of understanding. So really, this is the time to wake up. So I'm going to leave those things over here, leave those equations up, and talk about this notion of birth-death processes. So a birth-death process is modeling a population. Okay, it's modeling a population of people or animals or whatever, or birth and death in a queue. So what happens in a queue? So you go to your Tim Hortons and you join the queue. We'll think of that as a birth. And you get served and you leave the queue. We think of it as a death. Okay. Alternatively, we can think of a population of, I don't know, spiders in your house. So spiders get born, spiders die, presumably either of natural causes of being eaten by other spiders or hastily placed book on queuing theory. Boom, whoops, one less spider, that's a death. So we have these birth-death processes going on. And historically, one of the bases for queuing theory and studying queuing theory was the study of population sizes in the 1870s and 1880s. You know, biologists and mathematically oriented biologists started looking at how can we model populations, how do they grow. Remember I said queuing is a study of transient systems. Populations, of course, are not transient, right? But they grow and they shrink, and we want to understand how they grow and shrink, and these are related to birth-death processes. If we put our Markov chain hat on or stochastic process hat on, look at the birth-death process, we can immediately think of a state as being corresponding to a population size. Okay, so when I say that, you know, Markov chain is in state J, means that population has J members. Okay, that is the way we study this. All right. Then we can start thinking about the following. What are the allowed state transition probabilities in a population? In a birth-death process, we can say the following. Pj, j plus 1 is not equal to 0. Okay, P, or maybe I should be more precise. Okay. In a birth-death process, from state J, you can only go, put go in quotes, to states J minus 1 or J plus 1. And this is a death, it's a birth. Okay. If the process is Markov, if the birth-death process is Markov, it's assumption, then the fact that the population size is a particular value is independent of how it got there. Now remember, this is not going to be true in general. Okay? Let us say that we have reached a population size of 20. Okay? For some whatever reason, you're at 20. And let's say that this is a period of a lot of food available. The chances that you're going from 20 to 21, okay, births happening, are much higher than the chances of going from 20 to 19. Okay. However, if it's a time of famine, there's not much food available, the chances of going from 20 to 19 are much higher than the probability of going from 20 to 21. Okay. So in reality, these state transition probabilities can be time dependent and in fact can be non-Markov. Okay. So in other words, if I come to 20 from 21, then that might say, okay, I'm in a famine state, then I'm more likely to be in 19, for example, whereas if I come to 20 from 19, I'm more likely to go to 21. So we can definitely have in real systems non-Markov properties. However, we will ignore it. Okay, just for the sake of modeling, we're going to say that if I get to 20, I can forget where I came from. Okay, I can tell you the transition rates. This will be time dependent or time independent. If it's time dependent, I have a non-homogeneous continuous time birth-death process. But if it's homogeneous, then I can tell you, okay, this is it, right? So in many cases, we can assume Markov and just tell you the transition rates and say in famine time, this is a high rate, these going down a high rate, going up a small rates, and that's okay for this time. So it's still assumed to be Markov, and you can kind of mess around with the rates to model it. But you should remember that things in real life may or may not be Markov. But assuming it's Markov, then it's still continuous time. There is no clock that says you have to go, births happen at this time. Okay, you join the Tim Hortons queue, you join it at a random point in time, the continuous valued interval rather than the discrete time interval. There's not a clock saying join now, you're going to join at 10. So clearly it's a continuous time Markov chain. However, we have these constraints on the transitions, and what we can say over here is that I would just how am I going to do this? Okay, so I'm going to define these in terms of transition rates. Okay, so Qij is just Pij delta t. I'll say that Qij equals 0, okay, if j is not I minus 1, I, or I plus 1. Okay, if it's Qii, then of course it's your negative rate. But ignoring that for now, if Qij is equal to 0 for all other, in other words, there is no transition. The probability as well as the transition rate to go from state 1 to state 3, for example, is 0. Okay, so this means that we can draw the continuous time Markov chain in a very simple way. We have some state 0, all right, and then we have some state 1, state 2. Now, what I'm going to draw on these arrows is not the probability. I'm going to draw the rates instead. Okay, I'm going to draw the Q01. This is Q10. This is Q12, Q21. These are the transition rates. And the reason why I want to do transition rates and not probabilities is because these values can be plugged into this theorem here to give me the steady state or stationary transition probabilities of being in each state. Because of the continuous time case, I'm not doing probability, I'm doing rates. Okay. Moreover, there is a notational convenience. Whenever we have a rate Qj, j plus 1, this is represented by the value lambda j. Okay, and Qj, j minus 1 is called mu j. This is just notation, and it can be thought of that lambda j is the rate at which we go from j to j plus 1, and mu j is the rate at which you go from j to j minus 1. So in this case, this one will be called lambda 1 equals Q12. This Q10 will be called mu 1. Remember, it's going out of 1. Coming in from 2 is going to be called mu 2. This will be called lambda 0, etc. Okay? And of course, mu of 0, okay, well, it's going to be 0. There's no way to get below 0, right? And of course, lambda 0 is defined, but mu 0 is not defined. Okay, now notice that this is actually an infinite population size. I'm not saying that the chain is finite. I'm saying the chain is infinite. However, the transition rates, not probabilities, are the ones that are shown over here. Okay. Are there any questions about this? Okay. So, going back to the queuing model, or what happens is there's nobody in the queue. With some rate lambda 0, a customer arrives and the queue has 1, and then with some rate lambda 1, you come in, another person comes over here. Now, if they get service, they go out over here. Now, there's a term called in the queue, and there's something called in the system. Okay, and these are two different things. I probably should explain that. And in the system. Okay, so when the population size is 1, okay, let's look at it over here. When the population size is 0, nothing is happening. There's nobody there in the queue or being served. When the population size is 1, that person is being served with rate mu1, right? If somebody else arrives, they're not being served. They're in the queue. Okay, so in the system, okay, is basically in the queue plus 1, or number in system equals number in queue plus 1. Okay. In other words, number in system includes the person who is being served. Okay. And in some systems, the person who is being served is not in a buffer. In other systems, they are. Okay. So For example, in the Tim Hortons, the person being served is at the head of the queue. They're actually getting service. So if you look at the total number of people occupying space in the corridor, that includes everybody. That's number in system. Whereas in a network, in a networking router or a switch, we have certain number of buffers, and then we have a line card which has its own buffer, which is a packet in service. And so the packet in service is not part of the buffer. We call it total number of packets as being number in system, whereas the number in the queue will be essentially one less because it's being served. Okay. This technicality shows up in some places, but not just to know about it. All right. So I have a few minutes. I'm going to actually show you how we can use this and this to write down the stationary probability of a birth-death process. Remember, I did all this work. I did all this work in the last 2.5 lectures to get you to this equation. So now I'm going to show you how to use it. And well, we can use it quite easily because we know that the only rates which are non-zero are these two rates, mu j and lambda j. So first of all, let's get something out of the way. So qii, or jj if you want, okay, is going to be what? Well, we know that qjj plus qj minus 1 j plus q j plus, let me see, no, q, I want to do this properly. So qj j plus 1 and q j minus 1 j. Okay, let me do this properly. I want to do this one over here. Okay, I wanted to basically say sigma j q j k equals 0. All right, so let's write that down. So q jj plus q j minus 1 plus q j plus 1 equals 0. All right, so q j minus 1 is equal to, by definition, q j minus 1 is mu j plus, and that's lambda j equals 0. How did we get this equation, by the way, or that equation? That just comes from the definition of pij. We know that sigma j pij equals 1. And by definition of the qij's, which I just erased, we get sigma q jk over j is equal to 0. And that means that this equals 0, which means that qjj equals minus of lambda j plus mu j. Okay? So that's just, you get that for free, essentially, just to make sure that you're keeping track of that. How about the stationary distribution? So there's a time evolution of a birth-death process, which is basically given by the d. We can look at the d pi j by dt from the previous equation, but you don't learn a whole lot about it. Time evolution is not something that we really care about. So we're going to skip straight to the stationary probability distribution, which is given by this one over here. So the stationary probability distribution of a birth-death process, we just get over here 0 equals minus lambda j plus mu j plus lambda j minus 1 pj minus 1 plus mu j plus 1 p j plus 1. Just give me 1 second over here. 0 equals minus lambda 0 p 0 plus mu 1 p1 sigma j pj equals 0 pj equals pi j. Okay. So again, by convention, when we talk about birth-death processes, we replace pi j by pj. I just think people got fed up getting into symbols, and writing their LaTeX or whatever it is. So we just say pj equals pi j. So nothing has really changed. So in this equation, we just replace pj with pi j with p. And since all the k not equal j values over here cancel out, this becomes 0, other than for j plus 1 and j minus 1, this gives us right away this equation over here. 0 equals minus lambda j plus mu j. This we recognize immediately as qjj. That's this term over here. And I seem to have messed out the pj over here. Okay? So that's the first term. And then that summation gives us two more terms. Okay, this is sigma j not equal to k, qkj pi k. Okay, and you can verify that in fact it gives you those two terms. So we get this equation over here, and then the for the 0th state we have to do something special, because for the 0th state we don't really have the we don't have mu 0. There's nothing coming out of here, right? So we've got to take that into account by just simplifying lambda 0 p0 plus mu 1 p1. This gives us a set of equations, linear equations, in unknowns which are p1, p0, p1, pj, etc. And it turns out if you solve them, what we'll get is the values of p0, p1, p2, which are the stationary probabilities of being in state 0, 1, 2, etc., which is the stationary probability of being in this, which means the stationary probability of having a population of some size. So if I write down this over here and I annotate it with the lambda and mu, the rates of transition from one state to the other, then by plugging this into here, I can tell you the probability that are going to be in each state. Okay, just to give you some intuitive understanding of this, let's say that the lambdas are higher and the mu's are lower. We're going to be pushed out over here. Okay, so we'll have essentially an increasing population. So steady state probability is going to be a fairly large value of population. If mu's are generally larger than lambdas, you're going to push back over here. Now, we have to be careful, that we don't have an infinitely exploding population size. This is like a queue that grows on forever. Queuing theory doesn't say that the queues are going to be finite or bounded, right? Why? Because this is an infinite Markov chain. I can have it as long as I want, okay? But in practical terms, we want to make sure that the queue size doesn't grow too large. And when we talk about MM1 queues, we will see how that works out. Okay, so I've got to roughly about page 20 here in the notes. I'm going to quickly review what I did today just so that you have an idea what's going on. And we're going to plunge right into birth-death processes last time. So we did a little bit on recurrence, and we know the important thing to remember is transient means there is some chance you won't come back, and if you are going to come back for sure, it's going to be recurrent. We looked at the stationary probability distribution and showed that there is the second theorem tells us a simple sort of plug and chug approach and a checklist, which tells you what to check for, and if those conditions hold, we can just find the stationary probability distribution for a discrete time Markov chain. And we then looked at the residence time in a state and found that it was geometrically distributed. And we looked at the continuous time Markov chain and the meaning of continuous time, what it means. You intuitively need to understand that. Stated some theorems. And we looked at one specific type of continuous time Markov chain, which is a birth-death process. So each time you can move from one state to another. It doesn't have to be in a particular clock tick. It can happen at any time. But we have the restrictions on what particular transitions are allowed. I covered the notion that what we have in a continuous time Markov chain is not transition probabilities or transition rates, which are defined over here as essentially Qij equals Pij delta t. The limit as delta t tends to 0. Okay, so it's sort of the infinitesimal rate at which we move from state we go from rate from state I to state j, so it's a limit. And then we use this in these set of linear equations to obtain the stationary probability distribution of a continuous Markov chain, continuous time Markov chain, which allows us to then write down the stationary probability for any birth-death process. And the stationary probability distribution is given by solving this set of equations where we really only have basically 3 terms for most states, and then you have 2 terms for the zeroth state, and this allows us to solve that. Okay. So in the next class, what I'll do is I will show you the matrix representation for this, and I'll make some things clear, and what's called the Q matrix, the transition rate matrix, do some example, and then we'll use this to study the behavior of a Poisson process, it's called a pure birth process, and also the famous MM1Q. So we should probably be able to do at least MM1 and perhaps MM infinity Q next class. Okay. All right, so I'll stop here for now.